Good afternoon, everyone.
Good afternoon.
Good afternoon.
Today is a review session for the exam tomorrow. So I sent an announcement. I said that I divided the exam into two parts. I did this one to make your life easier and do not feel stressed, but I don't like what I did is something you like or you don't like. Because I did this one because I don't like you to go over all the materials in one day. And also, I'm not going to ask you to do anything by R during the exam. So the exam will cover Unit 6, one population mean, Unit 7, one population variance, Unit 8, population mean and variance at the same time. And the exam, the in-class exam, will cover only these three. And then 9 and 10 will be at-home take-home exam. So today you need to cover only Unit 6, Unit 7, Unit 8. And for the take-home exam, you cover Unit 9 and Unit 10. I will ask you to do something by R. Something like, actually, I give you some data set, and I ask you to analyze the data set. So in this case, you don't need to go over all the materials at one time. And also, I'm not going to ask you to do something by R during the exam. And I give this one to, I feel like your life will be much better. I do not feel stressed, but I don't know what I did is something good or something not good. Please let me know.
So for the take-home portion, is that due the same night, or what's the process going to be there?
I will give you 24 hours. Is it enough 24 hours? You can finish it in only actually in 1 hour. It is some question similar to the question in the homework. And I uploaded the key answer of all the homework, actually. The homework 7, I uploaded the key answer yesterday. So again, the exam tomorrow will cover Unit 6, Unit 7, Unit 8. And I will not ask you to do anything by R during the exam. And then after you finish the exam, I will release the part 2. Part 2 is give you some data set and you analyze the data set. I ask you some questions and you answer only these questions about the data set using R code. So the R code is already on Canvas, but you need to modify it and then you submit it. So now you don't need to do anything by R during the exam. And also you don't need to study everything. You study only Unit 6, 7, 8. And at home, you can study Unit 9 and 10. So what do you think?
Yeah, it sounds fine.
Okay. So the in-class exam will be 50 points, and the take-home exam will be 25 points. And you can finish it actually. If I were you, I will finish it in only 1 hour because the R code already uploaded on Canvas. You just modify the R code, answer the question, done. And you upload it on Canvas. So it doesn't take much time. I give you 24 hours, but just in case you are not, if you are busy and you would like to work at the evening or the morning, it's up to you. Any other thoughts? Any other concerns or anything else? Any other question? The exam will be 3 questions because you will study Unit 6, Unit 7, Unit 6, Unit 7, Unit 8. So I'll give you a question about Unit 6, question about Unit 7, question about Unit 8. So 3 questions in the in-class part tomorrow. Each question about a unit. Okay? What do you think? Hello.
Yes, that's good. Thank you.
Okay.
Yeah.
So today I'm planning to go over Unit 6, Unit 7, Unit 8, that will be covered in the exam tomorrow. And then after you finish the exam, I will release part 2, and I give you 24 hours. And actually, this part is analyzing some data. I will give you some data set, and you analyze this data set based on the unit 9 and 10. Okay? So any questions before I start going over the unit 6, 7, 8? Some question, what is the percentage of the 2 parts? As I said, part 1 in class tomorrow will be 50 points. And the take home will be 25 points. So in total, 75 points, the exam. So tomorrow will be something like 67%, and the take home will be 33%. Okay. Any other questions? We will have, as I said, we will be submitting our code. You don't need to submit the R code, but if I were you, I should submit the R code, because if I see something wrong, I want to make sure why your output is wrong. There is something wrong. So if I were you, I will answer the whole take home, and then I will upload the key and the R code file. If I were you. But if you are sure that your answer is correct for the take home questions, you don't need to upload the R code. But again, if I were you, I will upload the R code. Because when I grade, if I see something very strange outputs, I will look at the R code. If there is simple mistake, I will ignore this one and so on. Any other questions? Okay, so let me go over unit 6, 7, 8. And if you have any question while I'm going over this unit, please let me know. Second. They changed some stuff in Zoom. Okay, do you see the white screen?
Yeah.
Yes.
Okay, great. So let me start. Unit 6. Unit 6. This one is population mean mu. Population mean, which is mu, estimation and inference. Estimation and inference. Assuming sigma square is known. Assuming the variability of the population is known and the population mean is unknown. So what is the estimation of mu and the inference about mu using Bayesian approach and frequency approach? We covered the frequency approach very quick, and I told you that the frequency approach uses the likelihood. And the likelihood of mu given sigma square is known, and the data is collected from y1 up to yn. This likelihood proportional to e to the power -1 divided by 2 sigma square. sum of yi minus mu square. This is the likelihood. And then in the frequency approach, they use the maximum likelihood estimation. They take the log of the likelihood, and then take the derivative of the likelihood with respect to mu, and then set equal 0 and solve for mu. And they found that mu hat is the estimation of mu hat is y bar, which is the sum of yi divided by n. This is the frequency approach estimation of the population mean, assuming sigma square is known. But the Bayesian approach is different. In Bayesian approach, we use this same formula again. Bayesian approach, which is the posterior distribution of the parameter I'm interested in, which is mu in this case, given sigma square and mu proportional to the likelihood of mu given sigma square and y, the vector of y, times the prior distribution of mu. So we use this formula all the time, that the posterior distribution of the parameter I'm interested in proportional to the likelihood times the prior distribution of the parameter I'm interested in. And the prior distribution of mu can be conjugate prior, can be Jeffreys prior, can be conjugate prior, can be Jeffreys prior. Jeffreys prior is non-informative prior. The Jeffreys prior for the population mean mu is proportional to 1. So just plug in 1 for this one, for the prior distribution of mu. And the conjugate prior is normal with mean mu 0 and variance sigma 0 squared. So how they came up with this conjugate prior? Why they use normal? Because when they looked at the likelihood, they found the likelihood is kernel of normal. Is kernel of normal. So they found the likelihood is kernel of normal. So they use the prior distribution of mu normal. So when I multiply normal by normal, I get the posterior distribution is normal. So they found the likelihood is normal distribution with mean y bar. Hello? Any question? Okay, they found the kernel is normal with mean y bar and variance sigma squared divided by n, or in terms of precision, it is 1 divided by n tau square. And tau square is 1 divided by sigma square. So under this one is the posterior distribution is what? Under this one is the posterior distribution is what? Let me write it down. Under the conjugate prior, mu 0 and sigma 0 square, the under normal mu 0 and sigma 0 square as prior distribution for the population mean, we found the posterior distribution of mu given sigma square and y vector of data as normal distribution with mean ny bar tau square, ny bar tau square plus mu 0 tau 0 square all divided by n tau square plus tau 0 square. This is the mean, the posterior, this one is the posterior mean, posterior mode, posterior median of the population mean. So this is the estimation of the population mean. And the variability is 1 divided by n tau square plus tau 0 square. And again, what does T0? T0 square is 1 divided by sigma 0 square. What is T square? It is 1 divided by sigma square, which is known value, assuming it is known. Under Jeffreys prior, the posterior distribution, probability of mu given sigma square and y It is normal with mean y bar and variance 1 divided by n tau squared. So this is the posterior distribution of the population mean mu, and you plug in tau 0 square is what? Y bar is what? N is what? Tau 0 is what? Tau square is what? And you get the mean and variance of the population, the posterior distribution of the population mean mu. And now you can use this posterior distribution for anything you want. You can use it to estimate the population mean. You can use it to do inference, to get confidence credible set, or do test of hypothesis. You can do whatever you want using the posterior distribution. So, but the idea, the question here we need to answer is what? Is how do I get these two values? Yeah, if I use the conjugate prior, how do I get mu 0 and sigma 0 square? If I use Jeffreys prior, it's fine. It is proportional to 1. I plug in 1 in the formula. But if I use conjugate prior, how do I select mu 0? How do I select sigma 0 square? But actually, it is very simple. There are many ways to select mu 0 and sigma square. So how do we select mu 0 and sigma 0 square? There are many ways. You can use previous study. You can use previous study. From the previous study, you can find mu 0, which is the sample mean of this study, and you can find sigma 0 square, which is the variability of the data in that study. So maybe there is some previous study, and they collected data about y, and use the mean, the sample mean of y, use the variance of y as the prior parameters of the population mean, or the prior distribution of mu. Or you can use the idea of the equivalent sample size, the idea of equivalent sample size. What do you mean by this one? I mean, maybe I would like to select a prior distribution for the population mean, and the information in this prior distribution is equivalent to a information in a sample of N0. And N0 equal tau 0 square divided by tau square, which is sigma square divided sigma 0 square. You can use this formula. Like maybe I say that I would like to assign a prior distribution for the population mean that has information equivalent to the information of a sample of 100, and sigma square is known. Let's assume sigma square is known as 10. So 10 divided by sigma 0 square. So now you can select sigma 0 square as 10 divided by 100. So this is how I select this one. What about this one? This one you can set this value as a researcher, like most probably the mu 0 as a 7. So how much you feel confident about 7? This is the sigma 0 square. So you can use previous study. It's very simple. You find the sample mean of this previous study and equal mu 0, the sample variance sigma 0 square, or you can use the equivalent sample size idea, or you can graph many normal distributions. And select the one match your beliefs, or you can use the idea of the 95% probability interval. And there are many other ways, but those are the very famous ones. And then once you get the posterior distribution, this one, after you select mu 0 and sigma 0 square, and you know sigma square, and you have n, y bar of the current data, plug in all the values, you get this value and this value. So now you have the mean and variance of the posterior distribution. Once you have these two, you can use this posterior distribution to do whatever you want. You can do inference, you can do estimation, it's up to you. So you can find credible set using Q norm function, but I will not ask you to use these kind of functions during the exam. And you can find the probability of H0 and probability of H1, and you compare these two to decide which one most probably correct. Like maybe you have H0 that mu is greater than 3 versus H1 mu is less than 3. It doesn't matter if I say equal or not, because it is a continuous and a variable. So you can calculate the probability of H1, probability of H0, and you compare and you take a decision. Or you can calculate the Brier odds, posterior odds, and you divide the posterior odds by the Brier odds, you get something called Bayes factor, like posterior odds divided by Brier odds, and take a decision based on the Bayes factor. Or you can take a decision based on the posterior odds, or you can take a decision based on the prior probability of H0 or probability of H1. And how do I use the function for estimation? How do I use the posterior distribution, this one, in estimation? This one actually is the posterior mean, posterior mode, posterior median, because it is normal. And this one is the posterior variance. So it's very simple. Estimation is very simple because this value is posterior mean, posterior mode, posterior median, and the other one is the posterior variance. And you take the square root, you get the posterior standard deviation. So this is what we have covered, unit 6. Any question? Oh, there is one more we covered as the posterior predictive distribution. Posterior predictive distribution. The distribution of y nu given y is normal with mu1 and sigma 1 squared plus sigma squared. This is the known one, known value, and this one is the posterior variance. You already calculated. And this one is the posterior mean. So if I'm going to select a new, I'm going to measure a new observation or measure a new participant. And what is the probability that the value I measured is greater than some value or less than some value or between two values? I can use this posterior predictive distribution. I'm not going to ask you to calculate any of these kind of things during the exam by R. And actually in the exam, part 2 of the exam, I will not ask you to calculate these kind of things because the part 2 will cover unit 9 and 10. Any question about unit 6? Any question about unit 6? Okay, unit 7 is the same. We follow the same approach, but for the population variance, assuming the population mean is known. So unit 7 is population variance. Sigma square, estimation and inference. Assuming mu is known. Sorry, mu is known. Assuming mu is known. So what is the estimation of the population variance? And how do I get the credible set and do test of hypothesis about the population variance? Assuming that mu is known, we follow the same approach. First, the frequency approach, using the maximum likelihood estimation. The maximum likelihood estimation using the likelihood function, which L of sigma square, assuming sigma square is unknown, but mu is known, and the data, vector of the data is known. This one is proportional to sigma square as a random variable to the power negative n divided by 2 times e to the power negative 1 divided by 2 sigma square sum of yi minus mu square. And take the log of the likelihood, take the derivative with respect to sigma square, set equal to 0, and then solve for sigma square, and they found sigma square had the estimation of sigma square is the sum of yi minus mu square divided by n. This is the maximum likelihood estimation, but Bayesian approach is different. In Bayesian approach, we use the same formula again, the posterior distribution of the parameter I'm interested in proportional to the likelihood times the prior distribution of the parameter I'm interested in. So the probability of sigma square, the posterior distribution of sigma square, given that mu is known and the data is already collected, this one proportional to the likelihood of sigma square given mu and y times the prior distribution of sigma square. The prior distribution of sigma square, I can use conjugate prior. I can use Jeffreys prior. I can use Obenbach's prior, the very famous one. Obenbach's prior. Jeffreys prior is non-informative. Obenbach's is non-informative. Conjugate prior is informative. But the difference between Jeffreys prior and Obenbach says proper prior, but Jeffreys prior is improper prior. The conjugate prior is inverse gamma with alpha and beta. Why they use inverse gamma? Because when they looked at the likelihood, they found the likelihood is a kernel of inverse gamma. The kernel of inverse gamma was alpha n divided by 2 minus 1, and beta is n s squared divided by 2. Because they found the likelihood is kernel of inverse gamma, so the conjugate prior for the population variance is inverse gamma. So when I multiply inverse gamma by inverse gamma, I get posterior distribution inverse gamma. The conjugate prior is inverse gamma with alpha and beta. Jeffreys prior is of sigma square proportional to 1 divided by sigma square, which is inverse gamma 0, 0. It is improper because alpha and beta should be greater than 0. But for Jeffreys prior, it is alpha is 0, beta is 0. This is why it is not, it is improper. And in Obenbach's prior, they use inverse gamma with something greater than 0, but it's very close to 0, like 0.01, 0.01, or 0.1, or 0.001, 0.001, and so on. So when we multiply the likelihood by the prior distribution, we get posterior distribution inverse gamma again. So what is the posterior distribution under Jeffreys prior and the posterior distribution under the conjugate prior? Under conjugate prior, which is inverse gamma, alpha, beta, the posterior distribution of sigma square, which is probability of sigma square given mu and y. This one is inverse gamma, alpha plus n divided by 2, and beta plus n s squared divided by 2. Alpha and beta are the prior parameters of the conjugate prior. N is the sample size of the data you have. S square is the sample variance of the data you have. You plug in these values, you get alpha star, beta star, and now you can find the posterior mean, posterior variance, posterior median, posterior mode as estimation for the population variance sigma square. So you can use the posterior mean, let me write down the posterior distribution of sigma square under Jeffreys prior first, and then I give you the formulas for the posterior mean and variance for inverse gamma and so on. So under Jeffreys prior, the posterior distribution of sigma square given mu and the data is inverse gamma with n divided by 2 and ns squared divided by 2. From where I got this one? From this one. Plug in alpha equals 0, beta equals 0. You get alpha star n divided by 2, beta star is ns squared divided by 2. So whatever you use, Jeffreys prior, or use the open box prior or the conjugate prior, the posterior mean is the mean of the inverse gamma. And I always get inverse gamma. It will be beta divided by alpha minus 1. The posterior mode is beta divided by alpha plus 1. The posterior variance is beta squared divided by alpha minus 1 squared times alpha minus 2, and so on. So you estimate the posterior mean, estimate sigma square by the posterior mean, mode, and you calculate the variance, and so on. But the question now is, again, how do I get alpha and beta for the conjugate prior? If I'm going to use conjugate prior, if I'm going to use Jeffreys prior, it's easy, 0, 0. Open box is 0.01, 0.01. But what about the conjugate prior? How do I get alpha and beta using previous study or graph mini denses and so on? How do I select alpha and beta of the prior distribution? There are many ways again. You can graph many inverse gamma with different alpha and beta and see which ones match your belief, or solve two equations, function of alpha and beta. What do you mean? Because maybe I would like to set the prior distribution for the population variance such that the mean of the prior distribution is, and for example, the median or variance equals some value. And I know the formula for the mean of the inverse gamma is beta divided by alpha minus 1, so equal this value, and median is equal some value. I don't remember the formula. Equal some value, and then I solve these two equations, I get alpha and beta that satisfy two conditions, and so on. Or you can use previous study. If I have previous study, how do I use it to find alpha and beta? Alpha equal the sample size of these previous study divided by 2 minus 1 give me alpha, and beta is the sample size of this previous study times the variability of this previous study data divided by 2. This is how I get alpha and beta using previous study, and so on. There are many other ways, but those are the very famous ones. And again, I can get the 95% credible set using R, the Q inverse gamma, and also I can do some inference, like H0 is sigma square is greater than some value versus sigma square is less than some value, like some value. You can find the probability of H1 and probability of H0, and you compare these two and take decision. Or you can calculate the prior odds, posterior odds, and then you calculate the Bayes factor, which is the posterior odds divided by the prior odds, and then take a decision based on the Bayes factor. So we follow the same approach for the population mean, given sigma square is known, and this one is the population variance, given mu is known. And then unit 8, we worked with these two parameters, both of them are unknown. Mu is unknown, sigma square is unknown. But before I cover this one, do you have any question about unit 7? Any question about unit 7?
Just one quick one.
Sure.
Can you just tell me really quick, remind me really quick what S squared is in this case? You said variability.
S square is the sample variance, which
Okay.
is the sum of yi minus mu squared divided by m.
Okay, thank you.
You're welcome. Any other questions? Okay, unit 8. Estimating mu and sigma square simultaneously and inference. Using frequency approach, sigma square is the sum of yi minus mu squared divided by m, and mu, estimation of mu is sum of y divided by n, is the same thing. In Bayesian approach, we use the same formula again, the probability or the posterior distribution of the two parameters mu and sigma square given the data proportional to the likelihood of mu and sigma square given data times the prior distribution of mu and sigma square. And assuming they are independent, this one can be written as the probability of mu times the probability of sigma square. As before, there are many ways to select probability of mu. There are many ways to select the prior distribution of sigma square. You can use Jeffreys prior, you can use inverse gamma, you can use open box prior. The same thing for this one. The Jeffreys prior, the normal mu zero sigma zero square, and so on. When we used normal with mu zero and sigma zero square for mu and inverse gamma, alpha and beta, and multiply these two with the likelihood, we got the same formulas of the posterior distribution of mu given sigma square and the posterior distribution of sigma square given mu. But they depend on each other, because in the unit 6 and 7, each time we assume the other one is constant. But it depends if they are, both of them are unknown, they depend on each other. So this is why, because they depend on each other, there is no closed form for each, depends on only the parameter. So we use Gibbs sampler. And before we go, when over the Gibbs sampler, we cover the idea of conditional distributions. So we found that the conditional distribution of sigma square is inverse gamma, probability of sigma square given mu and y is inverse gamma with alpha star, alpha 0 plus n divided by 2, and beta star is beta 0 plus 1 divided by 2 sum of yi minus mu square, which can be written as n s squared divided by 2 again. It is the same formula. And the conditional distribution of mu, probability of mu given sigma square and y, is normal distribution with ny bar divided by sigma square plus mu 0 divided by sigma 0 square, all divided by n divided by sigma square, plus 1 divided by sigma 0 square, and variance is 1 divided by n divided by sigma square, plus 1 divided by sigma 0 square, which is exactly the same when using the precision. Normal n y bar tau square plus mu 0 tau 0 square divided by m tau square plus tau 0 square, and 1 divided by n tau square plus tau 0 square. It is the same formula. But keep in your mind, this one depends on mu, and this one depends on sigma square. The sigma square given mu given sigma square. So they depend on each other when both of them are unknown. So the idea is what? You can use Gibbs sampler, or you can coding the problem. But I'm not going to ask you to code the problem during the exam. But the idea is you set two initial values, one for mu and one for sigma. You plug in the initial values of sigma square in the posterior distribution. You plug in the initial value for sigma square in the distribution of mu, and then you randomly select a value from randomly generate a value from the distribution of mu, and then you plug in this value in the distribution of sigma square. And then you randomly select a value from sigma square, and you do it many times. And you get a random sample from the posterior distribution of sigma square given mu, and the posterior distribution of mu given sigma square, which you will find that after some iterations, like 100 iteration, 1000 iteration, the value you generate is not from the conditional distribution, it is from the exact posterior distribution. There is some proofs of these ones, but we do not cover proofs in this class because it is applied course. So when I should start generating these kind of things, or so you can check something called convergence. And you can use many things. You can use the trace plot. You can look at the Gellman-Robin diagnosis, or you can look at the standard error, which should be less than the standard deviation divided by 20, or you can look at the effective sample size. Or you can look at the autocorrelation plots. For the trace plots, I need to look at the change to be mixed well. It's not something like each chain go up and down in a different area. They should be mixed well. For Gellman-Robin, the red line, which is the variability within divided by the variability between divided by variability within, should be close to 1. And the standard deviation, or you can look at the standard error, should be less than standard deviation divided by 20. Or you can look at the effective sample sizes. The effective sample size should be a few thousands. Although maybe you generated 100,000 values, but the effective sample size may be something like only 5,000 or 7,000 and so on. Or you can look at the autocorrelation to see how much variability, how much randomness in the generated random samples. So this is unit 8. And unit 9 and 10 is comparing two population means and comparing two population proportion. These 2 units will be for the take-home exams. And then we cover simple linear regression, multiple linear regression, but I'm not going to cover simple linear regression and multiple linear regression in the exam, whatever in class or as a take-home exam. I want to help you as much as I can to do great in exam 2 as you did in exam 1. So simple linear regression, multiple linear regression will not be covered in the exam, like unit 11 and unit 12. And the in-class exam tomorrow will cover chapter 6, unit 6, 7, 8 only. The take-home questions will cover only unit 9 and 10. Any questions? Any questions? Okay, I'm done for the materials that will be covered in the exam tomorrow. And if you have any question, please send me email. Okay. Any question again before you leave? Okay, have a great evening. And I will upload this recorded lecture on Canvas. Thank you.
Thank you.
Thank you.
Thank you.